Okay, we're going to start Voltaic Cells here. All right. Sorry, I'm starting a little late. I had to get a sample problem on there. This has not been showing up well. I don't know why. But this really isn't. What's going on with my... Oh, probably that whole please change filter thing that I've been ignoring all year. I'll bet it's finally coming back to bite me now. Okay, so, well, hopefully you can kind of see this. I'll tell you what it says if you can't see it all that well. Yeah. I'm recording. Actually, this won't make any difference for the video. It'll just make the difference for the people who are here because you won't be able to see it, but it won't matter for what's on the video. All right. Anyway, so a Voltaic cell. This is basically taking redox and making it do things for us, do cool things that help us with lots of things. So here's how this works. Normal oxidation reduction, this is an example of one right here. You've got a zinc strip that you're putting into a copper solution. Okay? If you do that, you end up with what we used to call single replacement back in the day when we thought such things occurred, right? Yeah. So what's really happening here is actually a redox, right? There's an exchange of electrons that's happening. And this picture, if you could see it better, would basically be showing you that the electrons, so you're starting out with copper 2+ ions in this solution, and you've just got zinc, right? So that's the first part of the reaction. You've got zinc plus copper 2+. Okay? What you end up with on the other side, if you could see the color of this better, the copper is actually depositing on the zinc strips, so you're ending up with copper. And now the zinc is in the solution as zinc 2+. Okay? And that is a balanced redox reaction. Now, what's happening here, the zinc is going to a zinc 2+, so the zinc is getting what? Oxidized or reduced? We in agreement there? Yeah. Leo goes Gur. Lose electrons, oxidation, so that's the oxidation that's happening right there. The reduction is happening with the copper, okay? So that's the redox that's occurring. The electrons are going from the zinc to the copper, all right? That's how those electrons are flowing. Well, if electrons are flowing, we should be able to use that, right? Because what do we call it when electrons flow? What do we typically call that? Electricity, right? Okay, so why can't we use that for something, you know, maybe powering a light bulb or something like that? Well, the problem is this reaction, the way it's set up right now, obviously we can't use it that way because the electrons are flowing directly from the zinc to the copper. But what if we could sort of separate these two halves of the reaction from one another and force the electrons to go through something on the way? Well, then maybe we've got something like a Voltaic cell, okay? So instead of setting it up this way, that was a good one. Currently confused. Instead of setting it up like that, we can put a piece of copper into a copper solution, put a piece of zinc into a zinc solution. So now we've got the solid zinc and we've got the zinc 2+ ions floating around down in here. We've got the piece of copper and the copper 2+ ions floating around in here. And then we hook them up to wires so the electrons are free to travel. Okay? So the same process is going to happen. The electrons are going to go from the solid zinc to the copper solution, right? And so you're going to have extra copper that ends up plating onto the copper here. And the zinc, if you let it sit long enough, it's actually going to start to disappear, okay? Because it's moving, you know, electrons at a time through the wire. But what we've done here is we have made something useful because now there are electrons flowing through this wire and it can actually power something. Now here we just have it connected to a voltmeter so that you can read the voltage that's going through it. You got a bunch of these, don't you? Yeah. So 1.10 volts, okay? But we could hook something else up to it, like a light bulb or something like that, and now we've got current flowing through a light bulb, and that as those electrons flow through it, then it's going to do something. All right, this is called a Voltaic cell. also called a galvanic cell. All right, same thing. Voltaic, galvanic. You need to understand those are synonyms. Synonym means they're the same.
We combine them.
All right.
Can we combine the two words and call it a volcanic cell?
No, you cannot call it a volcanic cell.
YOLO, do it.
That's something different. All right. Now, again, I know this picture is hard to see for those of you who are actually watching it because I really need to change my filter, evidently. But a typical voltaic cell is going to kind of look like this. And this is basically the same setup as we had on the screen before. It's just a little bit more high-tech. Or it's showing everything that's happening maybe a little bit better. Still have it connected to the voltmeter up here, okay? We've got a switch here that can either allow the flow of electrons or stop the flow of electrons, okay? So you can turn this on and off. But then we've still got the copper in the copper 2+ solution. We've got the zinc in the zinc 2+ solution. We've also got nitrate ions floating around in there, okay, because that's how we got the copper 2+. We put a copper nitrate solution, or solid, into water and made a solution. Same thing with the zinc nitrate on the other side here, okay? So this basically just creates a flow of electrons. And you can see here the electrons, like I said before, the electrons are going from the zinc to the copper, all right? And then they go through the copper metal into the solution. And when those electrons react with the copper 2+, they change the copper 2+ into solid copper. The copper gets reduced by the addition of electrons. And now, as you go, there's going to be more and more copper that starts plating out on this copper metal. Okay, so the copper metal is actually going to increase in mass. The zinc metal is going to decrease in mass. As the zinc that was over here in the solution part, it starts to go into the solution as zinc 2+ because it's losing electrons. Okay, but the main thing here, this is how you create a current, and this is how batteries are made. Okay, this is how batteries work. This is how we power the majority of the things that you use in your daily life. This is how your phone works, you know, very important piece of equipment.
They use lithium.
Okay, you're right. They don't use copper and zinc, but they use voltaic cells. So they use the same principle of the flow of electrons based on putting one chemical in one place where it's going to be oxidized and another one in another place where it's going to get reduced. Okay? All right, so here's the problem with this setup that we haven't really talked about yet, and I've been ignoring this middle part. But let's say that an electron flows from this solution into this one, okay? So now the electron has flowed into here. What's the overall charge on this side going to be compared to this side? That's an awkward way to ask that question. What happens to, you know, this side after 1 or 2 electrons flow through this circuit? This becomes more negative than this side, right? And this side's going to become more positive. Okay? Well, that's a problem because our electron's going to keep flowing through this thing if this side is more negative. Okay, we're good. Do electrons like to go from the positive side to something that's more negative? No, they have a negative charge. They're usually repelled by other negative charges. So as soon as this starts to become negative,
I thought that you like
well, not in this case. Sorry. So the electrons here, as they travel, make this side more negative. That's going to keep any more electrons from coming over to this side. So immediately your cell stops working, right? It worked for a second as the electrons traveled through, but now because this side is more negative, this side's more positive, now it's not working anymore. Obviously that's a problem because we want our cell to work, right? So what we do here is we create what's called a salt bridge, okay? And this basically just allows a way for the circuit to be completed, okay? So in that salt bridge, what you're going to do in your lab later on in the week is you're going to soak your piece of filter paper. This does not have to be high-tech at all, really. It just has to be a way for the electrons or the ions to get from one side to the other. So you can soak your salt bridge in sodium nitrate solution or something like that. So there are sodium ions in there and nitrate ions in there, okay? If this side becomes negative, the sodium that's inside that salt bridge is going to travel in this direction because the positive ions are attracted to the negatively charged solution, right? Then you've got the nitrate over here that's obviously going to flow to this side because it's negatively charged and it's attracted to the positively charged solution. In that way, these keep the solutions balanced as far as their charge so the electrons can keep moving through, okay? And so that's how a salt bridge kind of helps us to rectify that problem so that the electrons can keep going without changing the overall charge of either side of the solution. And then your current can keep flowing, and there you go. And they're saying it's usually a U-shaped tube that contains a salt solution. Like I said, a damp piece of filter paper works just as well, as long as it's been soaked in a salt, okay? All right, so the electrons leave the anode, flow through the wire to the cathode. I'm not sure if it's going to say it in here or not. There's some good news for you. They decided on the AP exam you do not need to label the anode or the cathode as either positive or negative, and that's good because it's always confusing, all right? So all you need to understand is what direction the electrons are going to flow, all right? Here's, I think, the best way to remember this. All right, my work here is done. See you guys next time. No, I'm just joking. I have to explain that. Red cat and ox, okay? If you remember those two phrases, I think this will help you. Reduction happens at the cathode, okay? Oxidation happens at the anode, all right? So if you can connect those two to one another, then you should be able to remember, because then you can kind of go back to Leo goes grr, and you can remember, okay, what's happening in reduction, what's happening in oxidation. I know that's a lot of steps, but I think that's the best way to remember it, okay? If you guys can come up with a better mnemonic, then let me know, because that's the one I've been using for the last few years. It's all I've got. So if reduction is happening at the cathode, then what's happening at the cathode? Reduction means what? Gaining electrons. So the cathode is where the electrons are being gained. That's where the electrons are going to, all right? Anox, so at the anode, oxidation is occurring. So what's happening at the anode? That's where the electrons are being lost. Okay, so they're going from the anode to the cathode. That's the flow of electrons, all right? Yeah, we kind of already talked about this. As the electrons leave the anode, the cations form dissolve into the solution in the anode compartment. Well, maybe we didn't quite talk about that. So what you've got happening here, again, just to make sure this is making sense. So you've got the solid zinc here. Okay, we're going to call this side the anode because that's where the electrons are going from, right? So the electrons travel this way into the cathode, all right? So the anode part of this solution, what's happening is the zinc is dissolving and becoming Zn2+. Okay, it was solid zinc, neutral charge. It loses 2 electrons. Now it dissolves in the solution as zinc 2+. Okay, that's what's happening on the anode side. On the cathode side, you've got this copper 2+ that is now gaining the electrons that are coming through. As it gains those electrons, now it becomes just solid copper, and it starts to plate out on the metal. So that's why I keep saying, in a cell like this, in a voltaic cell, it will not run forever, right? Because eventually you're going to use up all of your solid zinc, and you're going to use up all your copper 2+ ions as well, all right? So eventually these things have to stop. Hence, a dead battery. Now, can you change it back? You should be able to run the reaction in reverse, right? But the reaction is only spontaneous in one direction. We're going to talk about all of this later. I'm just kind of giving you a preview here. But if the reaction is only spontaneous in the forward direction, then what do we have to do to get it to go back? Put in some energy, right? Then we can put it back, recharge it, if you will, recharge the battery, and then it will run again. See how that works? That's a battery. All right. As the electrons reach the cathode, cations in the cathode are attracted to the new negative cathode. This is still just a lengthy description of what I just showed you. So electrons are taken by the cation. The neutral metal is deposited on the cathode. So that's the deposition or the plating out that I was talking about on the copper that occurs. All right. So here's a sample exercise, and then we'll be done. Following oxidation reduction reaction is spontaneous. Kind of a long one. Solution containing potassium chromate and H2SO4 is poured into one beaker, and a solution of Ki is poured into another. Salt bridge is used to join the beakers. Good, we've got a salt bridge, so this should continue to flow. A metallic conductor that will not react with either solution, such as platinum foil, is suspended in each solution. And two conductors are connected with wires through a voltmeter or some other device to detect an electrical current. Resultant Voltaic cell generates an electrical current. Indicate the reaction occurring at the anode, the reaction at the cathode, the direction of the electron and ion migrations, and the signs of the electrodes. It's easy enough, right? I think we need a picture. All right? Pictures always help me with this sort of thing. So let's draw a picture here. In a typical Voltaic cell, we'll have these separated into two compartments, right? So let's just do two beakers here. Excuse me, chair. Sorry, I bumped into it and I thought it was Ben, so, and I was, have to have an awkward moment. I was going to apologize.
Why do you apologize?
Yeah, so I apologize to the chair instead.
Hypothetical apology.
Yeah, no problem. All right, so we've got one solution that has potassium chromate in it and H2SO4. Why is the H2SO4 there? Yeah, we need the H+, right? This needs to be an acidified solution. If it's not happening in acid, it's probably not going to happen. Or it's not going to happen this way, that's for sure. I still need to figure out what was happening with that peroxide. For those of you who didn't acidify it first, I do not know why that was turning brown. But there's some sort of different reaction that's happening there. That's for sure. All right. You really didn't need me to tell you that. Obviously, there was a reaction happening there. So this is our redox reaction, okay? So what we got to figure out, kind of looking at maybe oxidation numbers here, figure out where the oxidation is happening, where the reduction is happening in this thing. We've got platinum foil that's being used as the metallic conductor, okay? So that's suspended in each of the solutions. So I'm really not good at drawing these things, but we'll just put like a piece of metal suspended in each of the solutions, okay? There's the solution, and that's down in the solution, okay? So those are our two pieces of metal that's gonna serve as the anode and the cathode. A salt bridge is being used to join the beakers, so we've got something, the YouTube or whatever. YouTube. It has a different meaning in electrochemistry. That's joining these two things together, and that could be, anything. That could be NaNO3. We'll say it's NaNO3. Okay, inside this salt bridge. And the two conductors are connected with wires through a voltmeter. So we've got, I'm running into my words now. So we've got a wire, right? Or wires, rather. But I'm just going to draw this. Okay, so then we've got our voltmeter here. It's connecting the two of them so that the flow of electrons can happen there. Or some other device to detect an electrical current. Okay? So the reaction occurring at the anode, what is that really asking? Remember what I just showed you. Right, anox, right? So anode is the part of the reaction that's the oxidation. So here's where it gets a little tricky. We've got to figure out what's getting oxidized here. Can you kind of look at this thing and see the two species that are changing their charge, maybe? What is it that might be changing? Or I should say oxidation state, not charge. Okay, it looks like the CR might be, possibly. Okay, and then what else? Probably the iodine. Okay, So let's figure out what's doing what here. The chromium on this side needs to end up as a 2- overall. There's 7 oxygens, each with a 2- charge. So that's a -14, right? So the chromium, in order to balance that out, needs to be what? +6, okay? Because then you've got a +12 overall, right? So this has an oxidation state of +6 for the chromiums on this side. Well, obviously that's a change, because over here it's a 3+, right? So it goes from a 6+ to a, or +6 to a +3 for oxidation states. What is that? That's reduction. So that's not our anode reaction, that's our cathode reaction, right? So that leaves the iodine. Let's just double check and see here. The iodine has a -1 oxidation state on this side because it matches its charge. What about on the other side? 0, right? Okay? So it goes from a 1- or a -1 to a 0. That's oxidation, right? That's losing electrons. It's becoming more positive. So that's our oxidation. That's the reaction that's happening at the anode, okay? So at the anode, we've got, it says indicate the reaction occurring at the anode. So that's going to be the 6I- going to 3I2. Oh, I was just writing it off to the side. I guess maybe I should put it on the same side as, yeah, I was not being intentional about that. Okay, so 6I- 3I2. Okay, and then we need to put something on here to balance out the charges, right? We need to put 6 electrons on this side. So basically we're just writing the oxidation half reaction here, okay? So that's happening on this side, okay? And that's right, because the electrons are going to be flowing from this side to the cathode. As the electrons do that, this side is going to want to become more negative. The left side is going to want to become more positive. So then the NO3, since I put that on the left side of the salt bridge, the NO3 is going to want to go to that side. All right, so there's one half reaction. Reaction happening at the cathode is going to be the Cr2O7 2- going to Cr3+. Okay, this one we're going to have to balance. First of all, there's 2 chromiums on the left, so we need to put a 2 here. Okay, but then we've got 7 oxygens, so we need to add 7 H2O to this side. Now we've got 14 H pluses to deal with, and you could actually just look at the equation and see all of this, right? 7 H2O, 14 H plus, but I just thought I'd take the opportunity to remind you how this all works. And then we need to balance out the electrons. There's 12 plus on this side. There's a 6 plus on that side, so we need 6 electrons on the left, which works out rather nicely because we're losing 6 electrons on the left. We're gaining 6 on the right, so everything's good. All right? So that takes care of the reactions occurring at the anode and the cathode. All right? The direction of electron and ion migrations. Okay, so again, remember, the anode is where oxidation occurs. That's where the losing of electrons is happening. That's over here on the left. So the electrons are going to be flowing through the wire in this direction, right? Everybody okay with that? All right. The direction of electron and ion migrations. Okay, so the ions in our salt bridge, we already kind of talked about this, but the NO3 is going to come down into this solution because it's going to be attracted to the positive charge that starts to build up as the electrons flow. And then the Na plus is going to travel to this side because it's going to be attracted to the negative charge that starts to build up as the electrons come into the cathode. All right, so now we've got the direction of our ion migrations. The signs of the electrodes, that's the part you do not have to worry about anymore. They specifically said on the AP exam you do not have to label these with a positive or a negative. You just need to know which direction the electrons are flowing. Okay? So that's basically it. A little bit complicated, I guess, but I mean, this is the way that pretty much every voltaic cell is going to work. Okay? Does that make sense? All right. So we're done for the day. We'll see you guys in class.